My presentation will be on the engineering topic of semiconductors and optoelectronics, more specifically on virtual reality. However, the technologies mentioned definitely include areas from other topics as well. Virtual reality headsets were first created in the 1960s, but most significant developments were made more recently. The goal of virtual reality is for the user to experience the reality portrayed to be as close to the actual reality as possible by creating an immersive digital environment. As for the actual upgrades, there have been continuous innovations in its display/visuals, sound, mechanisms of interaction, and design. Through such upgrades, its applications have only continued to rise, especially for educational, entertainment, healthcare, architectural, socializing, and training purposes. I believe that with more of the electronics industry investing in technology related to virtual reality, its applications will only continue to rise and increase in accessibility. One of the greatest selling points of the VR headset has to be its display, especially as it comes closer to achieving the look of realistic environments. Major players in allowing these upgrades in display technology for the VR headset were said to be the Apple Vision Pro with their excellent OLED display, pushing the possibilities of the immersive visual experience that VR can provide, as well as Sony Semiconductor Solutions OLED microdisplay tailored specifically for VR. As for actual technological innovations in display, stereoscopic displays are definitely one of the main players. Through delivering different images to each eye, it allows for greater depth perception and thus a more realistic experience. Autostereoscopic displays is another display technology that allows for a more immersive experience. However, unlike stereoscopic displays, it is glasses-free. Through optical filters, it delivers right and left images. A few examples of specific optical filters that the related article mentioned were parallax barriers and lenticular rays, allowing for a greater viewing range and improved aerial perspective. A more recent type of display is the light field display, which replicates real life through mimicking 3D surfaces through bundles of light rays. It seems to be similar to holography, however, at the moment it is more compact and realistic, although it does have lower resolution and depth. Finally, despite VR's main usage being 3D, the core of 3D displays are ultimately 2D. Through liquid crystal lenses and anisotropic active lenses, the display adapts from 2D to 3D displays. Much like our smartphones, interface upgrades are important for ease in its usage. Touchscreens and buttons are definitely very useful for a lot of recent technologies. However, these are hard to implement into VR. While reliance on physical movement, whether it is through a controller or camera, has proved to show promise for recent VR technology, directions directly from the brain would definitely allow for more convenient control. And I feel investments in these technology could definitely be applied for many other future technology and potentially even technologies right now. Interestingly, there have been different types of interface options available that use the brain. One of them being the brain-computer interface, also known as BCI. BCI is a technology introduced at a similar time to the VR headset and has also seen a lot of recent advancements. It allows for direct communications between the external device and the brain, in this case the VR headset. Through the collection of brain signals, much like a button, it can allow for certain brain signals to execute certain commands. Motor imagery, also known as MI, is similar to BCI. However, it is specifically used to simulate movements of the body without the actual need to physically move. More specifically, it requires the user to use the area of their brain for movement without actually executing it. These signals from the brain are used to move in the virtual environment. Steady-state visual evoked potential, otherwise known as SSVEP, responds to flickering stimuli, which are brain responses evoked through flashing lights, which allows for precise user input. The P300 event-related potentials is similar to the SSVEP. However, instead of the use of flickering stimuli, it detects specific visual stimuli, which is useful for interface and more reliant on selection. Because of the nature of how these interfaces work, the accuracy of each method of these interfaces vary. MI and BCI showed moderate levels of accuracy in the 75 to 85% range. The article referencing this explained that the accuracy was raised with more training, which makes sense as it requires more specific brainwaves and not just stimuli in response to specific events. Thus, the SSVEP and P300 event-related potentials had higher accuracies as they rely more on distinct patterns in the brain. The SSVEP had an accuracy greater than 90%, while the P300 event-related potentials had a range of 85% to 95% for its accuracy. For latency, it showed similar results, with the SSVEP systems showing more real-time potential than the MI-based systems at the moment. The hopes for these interfaces through innovations in technology is for the BCI and MI-based systems to become more accurate, as well as the more bulky nature of these systems to become more efficient and smaller, much like the smartphones over the last few years. Another significant aspect that adds to making the VR experience as realistic as possible is through the tracking system of the headset. One of the major improvements to the VR headsets is definitely having the audio as a sensory modality. This means immersive sound that simulates directional audio, which allows the user to feel as if sounds are coming from different directions. Environmental acoustics, which is the change in sound vibration in different environments. For example, sounds made in a park would definitely be different from those in auditoriums. And sound propagation, which is the way certain sounds make in different mediums, such as water, air, and different solids. To go into more detail on the specific technology, head-related transfer function, otherwise known as HRTF, simulates how sound waves interact with human ears and head, which allows the user to hear sounds accurate to the direction. Another technology related to directional audio is a spatial audio engine, which renders 3D directional audio depending on specific virtual environments. Environmental acoustics and sound propagation rely on essentially a trial and error through simulation in real life or physics-based models, especially for the different mediums and ray tracing to calculate how sound waves would react in certain environments. However, the main challenges of creating as realistic audio as possible is the real-time processing required, especially as the user moves around, which will lead to changing in virtual environments and directional audio. Another challenge in creating realistic audio is the difference in perceived sounds from speakers of the headset itself, which would have to be relatively compact, as well as the actual environments the user themselves are in, while considering the virtual space as well. Another important tracking system is the wide area tracking, which will allow for the user to move around in their virtual environment without as much physical movement in real life. Which is why I mentioned earlier that VR interface related to direct brain communication can be especially useful through subtle visual cues or the use of controllers. These innovations in tracking make it especially useful for training and educational purposes, such as medical training, military exercises, and industrial safety protocols, and it doesn't require as much physical space, but it stimulates a relatively realistic experience. In fact, the technology allowed for 10 times larger virtual spaces than actual space used, and the immersive experience of VR allowed for 85% efficiency of actual real-world practices for all of the mentioned training and educational purposes, which was regulated through user completion of tasks, error reduction, knowledge retention, and transferability of skills tested. As for the insight and challenges, high-performance tracking systems allow for latencies lower than 10 milliseconds, as well as movement accuracies in the range of 1 to 2 millimeters. And finally, a frame rate of 90 FPS, which are all within range of viable usage in training. Finally, one of the greatest problems of the VR headset at the moment, which I personally experienced a lot as well, is its heat regulation. While at the moment VR headsets are very capable, with displays rivaling those of recent monitors, intuitive directional audio interface, and not being very bulky, the compact system uses a lot of energy, thus causing great output and heat. Unlike recent desktops, which have a lot of space for fans and other temperature regulating devices, the compact design doesn't allow for such devices, which unfortunately leads to the user becoming the heatsink as an unintended consequence. As it is a major problem with the recent VR headsets, different designs are being tested. A recent test done showed that initially the top surface area led to an increase of 5.6 degrees Celsius, and other areas such as the bottom surface, front surface, and forehead had a temperature increase in the range of 1.1 degrees to 2.9 degrees, which overall had 28.6% of the heat produced by the headset itself directly transferred to the user. After the addition of the copper sheet, the top surface had a reduction of 6.5 degrees, while other areas had negligible reduction in temperature. The enhanced heat dissipation is undeniable, with a major reduction of temperature in mainly the forehead, and the heat transfer efficiency, which had an increase of 61%. On top of that, the user had a 25% reduction of perspiration over a 90-minute period, and the microcontroller unit, which was closest to the top surface area, had significant reduction in thermal bottleneck. I believe that VR has major potential in its uses, especially as the use for training and education continues to become more significant, such as for real-life expeditions or increase in knowledge retention. VR is definitely one of the more exciting topics for me in the engineering field, and I hope to continue to see major improvements, especially for the brain-to-computer interfaces. And these are my sources.